Hello everyone, my name is Juan Rosiles. I'm in Engineering Architecture 2 class at Joliet Central. This is my final video of the year. This is my semester 2 final exam. Let me begin. This is my lamp project. For this project, I was tasked to create a lamp from either 3D printing, laser cutting, or implementing both of them. I started off by always looking at different models online and see what I can find to have some sort of inspiration. I mainly looked in Bamboo Lab and all the different type of images they have online. I was mainly inspired to do it by the Pixar lamp, but I knew I wasn't able to design this part depending on how difficult it became. So I used different images to reference my project. Once I finished the research, I started the sketchings. I started with using the base and the key features that would implement into my lamp, making it unique. Also, this stated the problem and my solution to it. Then I worked on dimensions of the light bulb, make sure to have every single dimension of each piece that it contains so I know how much to dimension my pieces. Moving on from that, I was able to start sketching the more difficult parts, which included the helix next, which are the part that will hold this part, the top part of the lamp. Also started dimensioning the bottom pieces, which are the connecting pieces that will go where the light bulb will. So as you can see right here, the light bulb right here will fit on top of right here, which will be secured down by the pieces that were dimensioned before, which is this piece that will hold the light bulb in place, and this piece will go into here, which will go in the back of this piece. Now I can start prototyping. The prototyping is important to see that each piece actually fits and it will work with how it's intended to. So these were the easiest parts to make. It was simple, didn't take that much of gluing and cutting. Then I moved on to the shell, which will hold the light bulb and let light shine in a unique way. So basically, it was this piece that will connect with this, which will go on top, and this will be held in the back. Once all the pieces were made, I was able to quickly assemble it, show any pieces that might have any mistake. I was to get a good portion of it done. I was only missing the helix lens, which was kind of impossible to make using cardboard. So I decided to just skip that and just make the top piece. Once I finished prototyping, I could start modeling. These pieces were pretty easy, straightforward. They're not too hard to make. The dimensions were kind of easy to make, and it's just like a whole circle, cylindrical shape. But then these pieces come into play. This wasn't hard, I would say, to dimension. I would just say that I had to adjust this so many times because of how fragile it was when 3D printing. And then this piece kept failing twice before I had to remove one of the helix so that I can 3D print this other one along was having more leaf springs. Because the thing is, this piece was at an angle because that's the only orientation that would allow it to 3D print. So when this was happening, is that it would move because of this piece right here. It will sometimes move out of the plate and it'll fail everything. Then for my top piece, I originally had it like this. I was mainly going for the pixel lamp. That said, I decided that this design was not optimal for me and I didn't really like it. So I switched to this second one right here based on how it looked and functioned. Now it's time for an assembly. Sport assembly, these are pretty straightforward. Easy to assemble, each piece fit where it's supposed to go. And the explosive assembly was pretty much easy as well. Just had to move some pieces apart. Now, time for the hardest and boring phase of the project, the drawings. Started working on this because I started a long time before my Skills USA competition PR, so I was able to get these 2 pages done right out of the park. And mentioning each and every piece took me a while, as so many can make tiny details that I need to add. So as you can see right here, there's a lot of dimensions right here. You can't really tell right here, but there's a lot of dimensions everywhere that you couldn't really see. So right here, right here, right here, There were even some dimensions that couldn't add because it would just be too many. So each piece had so many dimensions that it added more time to my project. And these were the far easiest. They've been by far the most easiest stuff to do in the entire project. So it didn't take me that long to make these two drawings. Now it's time for 3D printing. It's just playing the waiting game as we wait for each individual thing to 3D print. It took around 8 hours in total. And these were the final results. Next is the skills you say additive manufacturing problem. The problem was to design and 3D print a catapult or trebuchet that was capable of launching a Lego minifigure with accuracy and precision while maximizing the launching distance. The design requirements for this was transferring and transforming energy, stored energy, a locking trigger mechanism, stability and safety, and no fasteners. Research. Material properties. The key material properties in this was creep resistance, which is the resist to deformity. So basically, when 3D printing, plastic tends to, when there's so much tension on it, and you leave it like loaded into like a flex form, it's gonna want to stay at that form. So if you try to release it after being left for so long, it's gonna stay at that position. Then elasticity is the ability to bend, and fatigue resistance, flexural strengths, and tensile strengths. Research design. Design such we for research notes we put different design suggestions, flexible parts, and part thickness. Basically, we had already looked up different designs we can use. We mainly use this one as reference. We can depending on how far it went. Then we one thing called the different flexible parts. So we, as we can see right here, we had some lead springs. Then we also thought about doing some torsion springs, but we found out it was not optimal, and the lead springs had more results. And we also have to make a trigger release base, basically a piece that will just let us release the level, which allowed the bucket to fly. And we design a bunch of bucket and throwing arm. Sketching. The key sketches for this one was connecting rods, base connectors, and lead spring connectors. So basically, for our base design, we want to make like a triangle shape at an angle to have more flying distance. And for our base connector, it's a piece that we're trying to put 3 pieces into one so we can save on material. And where this piece would go is right here, right here, right here. And this piece right here will be our kind of like our stop block to prevent the bucket from flying all the way around and actually stop at the top distance, which will release it at the maximum height. And lead springs held with holder will hold our lead springs together. Sketching again here, we have the pins, the arms, and the base V1 and V2 concepts. So for the pins, it was pretty straightforward. It was just a pin that will hold all the pieces together, which will hold the arms, the lead spring connectors, and the lead springs. And then the base V1 and V2, we had different designs on how we want to do this. So at first we wanted to just make it as a piece that holds everything, even the lead springs. But moving on forward from this, we decided to scratch this and have the pieces individually. So each individual piece right here was by itself. Then we have the lead springs, launching arm, and bucket. These pieces were the most hardest to sketch because we didn't really know how to make lead springs. So we were kind of basing off what we saw on the internet. And for launching arm, it was kind of hard because of how we wanted to design it. We wanted the bucket to have the maximum amount of distance, which and wouldn't get stuck while launching. Now, as for modeling, we just made the design on a 20-degree incline, made it a triangle shape because this triangle is the most strongest piece in nature. Then for our final design, we have a circular hole here, which was allowed the launch arm to launch while not being able to stop. So what I mean by that is like basically it's gonna freely rotate. It's not gonna stop no matter what. It has enough tolerances so that it's loose enough to turn. Then we have a rectangle hose here that will hold our launching mechanism together and our base together. And we also have a stopping hole, which we didn't really use, but it was meant to stop the bucket from launching all the way, but we realized it wasn't necessary at the end. Then we have the arm. For this, we started with the arm being just like this, but we later decided to increase the thickness on it because of how fragile it was kind of becoming. So after a while, the lead strings were just starting to bend right here and become straight. So we have to increase the distance on that. Then we have the connecting rod ends. We originally had them like this, but we decided to switch to this because it added more. It was able to flex more and able to more easily be able to put into each of the holes for it. Then for the modeling for leaf springs, these were by far the most difficult part to model. We actually we did it on the first try, but it took us a while to design because we didn't know how much space to give it from each between each spring. Then after that, we also made an upper one, which we're gonna decide to not to use at the end because of how much time we had left and how much we actually made it work. So we scratched this at the end. Then it was trying to support legs. This is the piece that was supposed to be with the base V1, but we decided to scratch it, just make it each individual piece. And this was our first design that we're going for. It worked, but this piece it keeps falling out, and then the lead strings didn't hold in here together. So we switched the design to this one, which would work way better. And then it's the slide release mechanism. So this piece right here would go into here, and it would slide and hold the launcher with a little branch it had that will connect right here. We also made an alternative one because at first our piece was getting locked in place because of how it was set up, and it had pieces running into each other, which was they wouldn't allow them to go release all the way. So we decided to fix it by making a piece that was a little bit longer and it won't have at the maximum angle and more at a smaller angle. Then we have the model of the launching arm. Our original design was to have it lay flat on some ridges, so it will reduce the friction in it. We then switched it over here because we realized that it would kind of get stuck still. So we made it at an angle sitting up, and when we first designed this, we had only two holes. I mean, we had our first four holes. We switched to two holes because we didn't make the top springs at the end. So for dirty printing, it took around 4 hours and 54 minutes, using 125.26 grams in total, and costing around $3.55, using 0.65 kilowatts per hour. For a plate one, it contained most of the pieces right here was two bases, arms, lead springs, and different connecting pieces. We used PLA plastic. It took 2 hours and 31 minutes, using 57.12 grams, costing $1.51. And for the second plate, used PLA again, taking total 2 hours and 23 minutes, using 68.14 grams, and costing $2.4 money. Either were testing setup pictures. So for our testing setup, we marked the paces with these little stickers, and we put the catapult right at the back of it. Then was OZL. He would be at the end collecting all the results from it. So we were launching, and where the piece land at first, we would put the sticker and mark that place. So for testing results, each catapult had 5 trials. So what I mean by each catapult is that we tested the catapult with the smaller trigger release and the longer one. So the shorter one produced longer shots and more accurate. The longer triggers produced shorter shots and were not accurate but were faster to shoot. And this was the final product. In the end, we chose the smaller one as it had probably more good results. But yeah, we were able to place second place at State competition. We were happy with our results.